New Thinking Aloud is presented by the California Institute for Human Science, a fully accredited university offering distant learning graduate degrees that focus on mind, body, and spirit. The topics that we cover here. We are particularly excited to announce new degrees emphasizing parapsychology and the paranormal. Visit their website at cihs.edu.
Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello, I'm Jeffrey Mishlove. Our topic today is physics and consciousness. With me is Saul-Paul Sirag, who is the author of ADEX theory, how the ADE Coxeter graphs unify mathematics and physics. Now, Saul-Paul is an old friend of mine. I've actually done an in-presence segment in presence number 68 about him, and I'm linking to it right now in case you would like to check it out because it goes into some depth about his background. I'm very happy to be able to present him here on New Thinking Aloud. However, this interview is going to be something of an experiment for me because Saul-Paul does not travel, and he lives in Eugene, Oregon. So because I couldn't bring him here to Albuquerque, I've made special arrangements to interview him on Skype. And possibly if this works out well, it'll open the door for other more long-distance interviews on the new Thinking Aloud channel. Welcome, Saul-Paul. It's a pleasure to be with you.
Yeah, it's great to see this working again.
Yeah. I know it's taken a little bit to get the Skype connection where we want it for a good quality video. Let me ask you this question now. Some time ago, you were quoted as saying that the laws of physics are actually the laws of the mind because we don't know anything at all about the physical universe except what we know that's mediated through human consciousness.
Yes, well, that's the basic idea intrinsic to what's called the Copenhagen interpretation of quantum mechanics, which is still considered the standard interpretation. And especially, that's the point of view very clearly stated in John von Neumann's famous book on the foundations of quantum mechanics, published in German in 1933 and in English in the 50s. And he shows that the so-called collapse of the wave function ultimately must occur in consciousness. That's the only fundamental place where it can collapse. Here's why. It's because actually there's intrinsic to quantum mechanics, there's a whole chain, sometimes called the von Neumann chain, because when you do an experiment with a piece of equipment, let's say making some quantum measurement, the thing is that according to quantum mechanics, the measurement equipment itself is quantum mechanical. It's made up, after all, ultimately of things like quarks and other fundamental particles. So the whole thing, so the measurement system, the measurement device itself is quantum mechanical, and there would be a Schrödinger wave function for that, and we can have a whole chain of these things, and ultimately we worry about, well, is it the eyes that are looking at the equipment where the wave function collapses? No, it might be further back in the brain. And ultimately, it's consciousness itself that, because after all, the reading comes into our consciousness, and so it's according to von Neumann, and a follow up in greater detail in a way by Wigner, Eugene Wigner, both of them at Princeton, and they were buddies of each other. They'd gone to the same high school in Hungary. They knew each other quite well. And especially in Wigner's paper on Notes on the Mind-Body Problem, he really emphasizes this idea that consciousness is fundamental to reality.
Well, you're referring specifically here to the collapse of the wave function, but even when it comes to classical physics, without a wave function to collapse, we don't know anything about the world of classical physics except what comes through human consciousness.
Yes, that's true, and classical physics is really a sub theory within quantum mechanics, because quantum mechanics deals with physics at a more fundamental level than classical physics does. But yes, you're right that even if we think in terms of classical physics, that's the case. Now, long before classical physics was even well established and worked out, there were philosophers.
Before Isaac Newton, you mean?
Yeah. Well, I'm thinking specifically of Berkeley, who critiqued Isaac Newton.
Oh, okay.
But he famously said, "To be is to be perceived." Okay, meaning to be, and of course, quantum mechanics didn't exist. This is in the 18th century, the 17th century, actually. And in fact, once Bell's theorem, we'll go into Bell's theorem later, I suppose, but once Bell's theorem came out, and Clauser's experiments backed up the predictions of quantum mechanics and showed that the world was, as strange as quantum mechanics claimed it to be, then some people remembered this famous slogan, in a way, of Berkeley, called esse est percipi, which means to be is to be perceived, in Latin, of course.
Now, I just mentioned parenthetically, we're talking about Bishop George Berkeley, for whom the city of Berkeley, California was named.
That's correct. That's absolutely correct, because he wrote a long poem which has the lines, "Westward the course of empire leads its way." And it was a poem about the attempt to set up basically a university in the Western Hemisphere, which he attempted and failed at. But so he wrote this poem as consolation.
I see. Well, we remember him.
That's why Berkeley was named Berkeley, for that poem.
Another thing about Bishop Berkeley is he was, as I understand it, a British empiricist. And yet at the same time, he maintained that all knowledge is ultimately contained in the mind of God.
Yes, well, that was because he was in a way the most radical of the empiricists. He pushed it all the way, in other words, as far as it could go. And then he came up with this slogan, esse est percipi. So then one has to answer, well, what about when we're not looking? And his answer to that was, well, God is always looking.
Yeah. And
so therefore, God guarantees the reality of the world even when we're not looking. So now I would say that that idea is more taken up by the idea of universal consciousness, rather than necessarily a Bishop Berkeley type God figure.
Well, it seems to me if we're going to get into the essence of physics and consciousness, a good place to go from here would be to look at why it is that Einstein was critical of quantum theory.
Well, in a way that, quantum theory to a lot of people, other than Einstein, seemed strange, but like Niels Bohr famously said that if one hasn't heard is exposed to the details of quantum theory and it doesn't make his head spin, he hasn't heard anything.
Hasn't understood it, yeah.
Yeah. And Einstein definitely understood. He was a very smart guy, and he argued with Bohr for years and years and years, the famous Bohr-Einstein debates about quantum mechanics. Now, what Einstein didn't like were actually two different things. He didn't like the indeterminism of quantum mechanics because of the Heisenberg uncertainty principle, and he famously said, God doesn't play dice with the universe. Of course, his idea of God was just basically a kind of metaphor. Anyway, but the other thing that's in a way more interesting is that he also pointed out that there's a kind of spooky action at a distance implicit in certain quantum mechanical situations. And he wrote about this on more than one occasion, but the most important occasion was the paper in 1935 with Podolsky and Rosen, so it's called the EPR paper for Einstein, Podolsky, and Rosen. And in the spooky action at a distance quote is actually in a very interesting set of letters between Einstein and Max Born. They were very good friends, and they wrote letters back and forth about the foundations of quantum mechanics. That's what these letters are all about. And Max Born was very strong upholder of the standard Copenhagen interpretation, and Einstein was opposed to that. But they were good friends, and so they wrote these letters in a careful, gentlemanly way because they liked each other. And by the way, these letters were published in 72, I think, not 71, actually, when a translation of them into English became available, because they were writing these letters in German, of course. And so the spooky action at a distance and the famous quote about God doesn't play dice with the universe is in different Einstein letters to Max Born.
In other words, from Einstein's point of view, if spooky action at a distance were to occur, then that should be impossible. And so therefore, because quantum physics predicts spooky action at a distance, Einstein felt entitled to reject it.
Yes, and another interesting thing is that in his very short autobiography, he didn't use the word spooky action at a distance, but he used another very interesting term. He said it's as if the particles are in telepathic contact with each other. It's telepathisch, as the German. And then later on, actually in the same book, one finds in response to Max Born and other people, he says that he had recently run into another physicist who said that he was inclined to believe in telepathy, And Einstein said, well, you must be thinking more about physics than psychology. And the other physicist, who I think, by the way, was most likely, would, although, I have no clear evidence of this, but because of other things known about him, it is probably Wolfgang Pauli, was a very close friend and patient of Jung. So he would have been open to this sort of thing, very open to it, as a matter of fact. But another interesting aspect of Einstein's attitude about telepathy, is that he wrote an introduction to a book called Mental Radio by Upton Sinclair, in which he praises the experiments that Upton Sinclair and his wife were doing, which today would be called distant viewing experiments. And so, in effect, Einstein was willing to believe that there could be telepathy between human beings, but not between electrons. So,
okay.
If one puts all this together, that's the conclusion you come to. Telepathy between people is okay, maybe even people and dogs, or who knows, but between electrons, no, I won't go there, is what he says.
But now I think it's fair to say, due to the subsequent developments, Bell's theorem, Clauser's experiments that we'll talk about, we know now that Einstein was correct about telepathy between humans, but wrong in suggesting that spooky action at a distance or telepathy between electrons cannot occur.
That's right. And what we have a really good name now for this spooky action at a distance. It's called entanglement, which is, it's very interesting because this concept of entanglement actually goes back to Schrodinger's paper in 1935, which was actually a response to the Einstein Podolsky Rosen paper of 1935. So he's kind of rubbing it in to Einstein, saying, well, there's what's going on is something I call entanglement, and he went on for several pages about this, and he claimed that entanglement is the most characteristic aspect of quantum mechanics. Now, ordinarily, a physicist would say that the Heisenberg uncertainty principle is the most characteristic aspect of quantum mechanics, but Schrodinger felt that entanglement was even more basic, which is very interesting. And another interesting thing about that paper is that it of course, was published in 1935 in German, and in fact, it's a very long paper. It was published in 3 parts, a very long, detailed argument about the EPR situation, Einstein's thought experiment. And it was not translated into English until 1980.
Now, we should go into some detail on the nature of the EPR thought experiment.
Yes, yeah. Otherwise, what we're saying won't make much sense, I guess. Yeah. Okay, the EPR thought experiment has to do with particles that are separating from each other spatially, and in Einstein's version of this thought experiment, you measure the position of one particle, and you know immediately the momentum of the other particle who's far away, and he thought of this as a way of showing that the uncertainty principle that says that position times momentum has to be greater than or equal to Planck's constant, which is Heisenberg's uncertainty principle for those two dynamic variables. So his argument was a way of trying to show that the uncertainty principle isn't fundamental. And so the idea would be that fundamentally underlying this uncertainty of quantum mechanics, there's a realistic layer that's sometimes called a hidden variable, underpinning of quantum mechanics.
Einstein hoped that there would be hidden variables because that would make quantum mechanics hopefully deterministic.
Yes, exactly. Yes. Yeah, and not only that, but it's important to note that Bell's theorem, which came out in the 60s, it began in 64, and the experiments based on Bell's theorem showed that there's a contradiction between the idea of the hidden variables and the predictions of quantum mechanics. So what Bell did is he provided a way, he created what's called the Bell inequality, so that you could do an experiment and test which is right, whether the hidden variable theory is viable or whether quantum mechanics, as already worked out in great detail and understood, is correct. And the experiments clearly show, and there have been many, many experiments, starting with John Clauser, published in 1972, and in many other experiments after that, that are much more elaborate and in testing the idea. Mm-hmm. They all agree that quantum mechanics is correct, and the hidden variable theory that Einstein wanted just is not viable. Mm-hmm. So we're stuck with the strangeness of quantum mechanics. But an interesting thing is this notion of Schrodinger's of entanglement now is all the rage in among physicists, and applying it to such things as quantum computers, which many different laboratories are attempting to build, because a quantum computer would be able to calculate things that you couldn't possibly calculate with an ordinary computer. We're far from, at this point, I think we're far from having a real quantum computer, but given enough time, we'll have quantum computers probably. And there's also other aspects of this entanglement which is important, which is quantum cryptography, which is actively being used by banks in sending banking information over telephone lines and in other ways over distance. So that's an aspect of entanglement that is being utilized now. So, in other words, entanglement started out as, one could say, an embarrassment, especially for people like Einstein in quantum mechanics, and it's turned out to be a useful tool. So, in the kind of lingo of computer geeks, then that would be like saying it's not a glitch, it's a feature, is what they say. It's not a glitch, it's a feature.
I see. Well, this might be a good time to introduce some of the ideas that were written about by David Kaiser in his book, which features you quite a bit, How the Hippies Saved Physics, because, well, you and I were back there at Berkeley in the 1970s. We were roommates, and I remember how excited you were by the fact that John Clauser was doing an experiment to actually test Bell's theorem.
Yes, well, we were roommates or housemates back in 1973 when we were at the Institute for the Study of Consciousness, which is the institute that was founded by Arthur Young. Anyway, yes, I had learned about Clauser's work from Elizabeth Rauscher, who was a graduate student at Berkeley at the time, and about the time that we met, that I met Clauser. Elizabeth introduced me to him. Elizabeth basically engineered the idea of having Clauser involved in a discussion seminar that began in the spring of 1975 and ran for several years, and that we endlessly discussed the foundations of quantum mechanics and the EPR thought experiment and Clauser's experiments. Clauser was in the group and very active in the group. And that's what the book, How the Hippies Saved Physics, is all about. And the sense in which we saved physics is that we brought the idea of entanglement up front and center. We thought about applying it to all kinds of other offbeat things like telepathy and psychokinesis and so on. And all of these things are mentioned in David Clauser's very interesting book.
David Kaiser's
very interesting book. He spent quite a bit of time writing that book. In the process of writing that book, he interviewed all of the people involved, including me, and we sent him material to include in the book if he wanted to. And so it's well worth reading, I'd say. It's a very detailed description of what it was like back then to be working on something that was considered so offbeat that if you were a graduate student working on it, it was really considered hard for your career, that you probably wouldn't get a good position in a university somewhere. In fact, Clauser himself, who was a very good experimentalist, did the first Bell theorem experiment. He was a postdoc at Berkeley for 7 years, which, in other words, he himself couldn't get a good position for more than 7 years. Actually, he was actually a postdoc for 7 years. Now, usually a postdoctoral position is like a 2-year appointment, hardly any longer than that. And a postdoctoral position of 7 years is probably a record. And it's a record that proves the opposition at Berkeley to people looking too carefully at the foundations of quantum mechanics, because the idea was, well, quantum mechanics is strange and crazy, but the math works perfectly, and the predictions all work out perfectly. So rather than worrying about the foundations of quantum mechanics, you should just shut up and calculate, which is sort of the slogan that was thrown at people who wanted to look into the foundations of quantum mechanics. Now, people like Elizabeth Rauscher and George Weissman, who were graduate students there, they thought differently, and they engineered the setting up of this seminar, which went on, I said, for several years, and they were very active people in that.
Well, Clauser's experiments and the subsequent experiments have now shown over and over again that if you take two particles that originate together and then travel far apart from each other, they still act as if they're in communication with each other, and presumably instantaneously, meaning faster than the speed of light.
Yes. Entanglement is an instantaneous connection. Entanglement entails in this instantaneous action at a distance that Einstein complained about in the spooky action at a distance. That's, we don't use the word spooky, we just call it entanglement.
Mm-hmm.
But it is spooky in a way.
And one of your concerns, and certainly amongst parapsychologists, we've wondered, could this be the mechanism behind extrasensory perception? Can you use entanglement, in effect, to send messages instantaneously across the universe? And I gather the answer is, at least the tentative answer, is not yet.
Well, you see, one can generalize from particles. You said two particles that have been, together and move apart. No matter how far apart, they're still, in some sense, in contact with each other. Well, in a sense, the same goes for everything. Mm-hmm. Anything that's been in contact will forever be entangled. Once you shake hands with somebody, you're entangled forever, so to speak, or even talk to somebody. Presumably, Well, this is what the mystics of every culture say. All is one. Everything is connected. Yeah, well, this would be, a way of seeing this. But if you're a physicist or a mathematician, you want to see the details and that's something that I've been concerned with. That's why I've pursued the idea of hyperspace as being the location of everything that's going on, and actually physics today is very much a hyperspace physics. When I say hyperspace, I mean that's a space-time of more than the usual 4 dimensions, and in string theory. We have very specific ideas about the number of dimensions and how they function and so on. There are 2 different versions of string theory, in a sense. One is a 10-dimensional version, and the other is a 26-dimensional version. And then there are versions of string theory that put the 2 together. That's called heterotic string theory. And there are actually 5 different string theories, 2 of them being heterotic string theories. But in 1995, Edward Witten unified all 5 string theories as sub-theories of an overarching theory he calls M theory, and that's an 11-dimensional theory. In which the fundamental entities in M theory aren't even strings. They're 2-dimensional objects, ordinarily called membranes, and 5-dimensional objects. There's the fundamental aspects of M theory. Mm-hmm. And I've written in great detail about this in my book, ADX Theory, which was published in 2016. ADX theory has to do with the ADE Coxeter graphs, and the book shows how the ADE Coxeter graphs classify many different, 20-some so far, different mathematical entities, and they all are important in string theory. So I think of these Coxeter graphs as being the basis for string theory. It's the matrix that string theory exists in.
Now we're talking about group theory in algebra, are we not?
Group theory, yes. Groups in algebras. Well, first of all, finite reflection groups are the basis for the Coxeter. They're called Coxeter groups too, and that's the beginning of it. And of course, that was way back in 1935. There's that famous date again, 1935. But yeah, various algebras and all kinds of other mathematical things like catastrophes are classified by these things. And really interesting is that Heisenberg algebras are classified by the ADEs. I have a whole chapter on that in my book, Heisenberg algebras. And Heisenberg algebras exist in many different dimensions. The ordinary Heisenberg algebra is a 7-dimensional algebra, but you can have much bigger Heisenberg algebras than that. But they all are classified. Every single Heisenberg algebra has to correspond to one of these ADE Coxeter graphs.
Well, before we get too far
together,
Saul-Paul. Yeah, I'm concerned that we're moving so fast we may lose some viewers. And so I'd like to step back for a moment and talk about Platonism in mathematics and why these mathematical relationships are so important.
Yeah, well, one of the things that the classification of mathematical structures by means of these very, very simple Coxeter graphs itself suggests a kind of Platonic view of mathematics. In fact, I suggest in my book that the ADE Coxeter graphs are Platonic archetypes for mathematics, but
Meaning that they are ontologically real, that they actually exist, not in physical space, but they do exist.
Yeah, and they exist independently of us. That's a Platonic idea. And in mathematics itself, over the years, there of course has been a lot of very interesting work on what's called the foundations of quantum mechanics. In other words, quantum mechanics, foundations of quantum mechanics is something that has to do with the Einstein Rosen Podolsky stuff. But in mathematics itself, the foundations of mathematics was very much up for grabs throughout the 20th century, throughout much of the 20th century. In other words, what's the basis for mathematics? Is it something that we just make up as a kind of a game? Well, that was one of the ideas, and it was proposed by a very famous, very important mathematician named Hilbert, and that's called the formalist foundations of quantum mechanics, not quantum mechanics,
mathematics.
And then there's a logicistic school of Russell and Whitehead, and their idea was to derive all of mathematics from the axioms of logic. And they attempted, they spent some time in the early 20th century putting together 3 huge tomes of trying to show that at least some aspects of mathematics could be derived logically. And after the end of the first volume, they were able to prove that 1 + 1 = 2. It took that. And anyway, something very important happened in 1931. That's when Kurt Gödel proved that both the logicistic school and the formalist school were invalid because of a famous theorem called Gödel's incompleteness theorem. Now, what is left standing basically is the idea that mathematics is Platonic in the sense that what mathematicians are doing they're not making up mathematics. They're discovering mathematics that already exists. They're sort of like explorers exploring a mathematical Magellan-type realm. And one interesting implication of this, of course, is if there are mathematicians on other planets, then they would have discovered a lot of the same mathematics that we did. There would be an overlap. And presumably there would be things that we discovered that they didn't, and vice versa, and that would be interesting to find out. That would be an implication of the Platonic view of mathematics. That no matter where mathematics is being developed, ultimately one will find the same structures. Gödel himself was a very strong Platonist, and by and large, mathematicians today have a Platonic view of mathematics because of Gödel's incompleteness theorem, 1931.
Now, the other remarkable thing about mathematics is that it seems to fit so well the empirical observations of physics.
Yes, Wigner wrote a very famous the paper on that called the unexpected. Anyway, he's comparing mathematics and physics, and he's finding it strange that mathematics fits physics so well. Mm-hmm. And of course, my book, Addict Theory, is the ultimate answer to his question about why. In fact, the subtitle of my book is How the ADE Coxeter Graphs Unify Mathematics and Physics. Mm-hmm. So that's my answer to Wigner, who was, by the way, a very great physicist who knew quite a bit of mathematics. He was, for years, a professor at Princeton.
And we referred to Wigner earlier in relationship to von Neumann's idea about consciousness collapsing the wave function.
Yes, and referred to Wigner's famous paper, the Notes on the Mind-Body Problem, mm-hmm. where he employs von Neumann's idea and pushes very, very strongly for the idea that consciousness is basic to quantum mechanics, and therefore to reality.
But not just Wigner and von Neumann and Schrödinger, virtually all the founders of quantum physics held this view, did they not?
It was considered the standard view, and still is, actually. Mm-hmm. It's still considered the standard view, and the majority of physicists probably have that view, although there's, more recently, there are many different attempts to found quantum mechanics in a different way to get around this the strangeness. Like there's the multiple worlds version, that everything that can happen does happen, but in different universes mm-hmm. that somehow attach to each other. But one problem with that is that nobody has figured out a way of using that point of view to derive the probabilities that quantum mechanics finds necessary, and that's called the Born probability interpretation of quantum mechanics, so if you can't use Born's theory, then if you can't derive it from that point of view, then I think it's problematic. Although it's a very interesting idea. And then there are others like David Bohm's idea. He very strongly wanted to push Einstein's idea of the hidden variables. But I would say that Bell's theorem, and in fact Bell's theorem is partly based on Bohm's ideas, and Bell was very fond of Bohm's ideas, and Bell himself wanted there to be a hidden variable level of quantum mechanics, but the experiments show that it's not really that hidden variable theory is not really viable.
Well, let's focus for a moment now on a paper you wrote. In fact, it was published by me as an appendix to the 1993 edition of my book, The Roots of Consciousness. And we published your paper called Consciousness, a Hyperspace View, where you attempted to use the mathematics of hyperspace, and we're talking about group theory and the Coxeter diagrams and so on, to provide a mathematical basis for consciousness itself.
Yes, this is I wrote this in 1988, and Jeffrey published it in 1993 in the second edition of his book, The Roots of Consciousness. And it's a long paper, about 40 pages, and I went into great detail in applying the Coxeter graphs to hyperdimensional structures. And what I pointed out was that there's because of the relationship of these graphs to different mathematical structures, that there are certain overlaps between these structures that strongly suggest a kind of universal consciousness that underlies that is in the overlap area between two different mathematical structures. And in order to make that clear, one would have to show a diagram or something. I have the diagram, the Venn diagram of these structures in the paper.
Well, I'll project them.
Yeah, project
in the video. They'll be in the video. As you describe them, I'll put them up.
Yeah. It's actually, I actually propose a very specific algebraic structure called E7, and E7 refers to a Coxeter graph with 7 nodes, and it's related to many different aspects. It fundamentally, of course, corresponds to the E7 Lie algebra and Lie group. It's a 133-dimensional structure, by the way, all by itself, but it has a 7-dimensional substructure, which is called the Cartan subalgebra. And that Cartan subalgebra is basically the what I call the reflection space of that structure. You see, each of the ADE Coxeter graphs corresponds to a reflection space, because you have a set of mirrors in the space, mathematical mirrors that function very much like an ordinary kaleidoscope, actually. In fact, Coxeter calls them kaleidoscopes. They're hyperkaleidoscopes, hyperspace kaleidoscopes.
Because what we're looking at here are symmetries. Is that correct?
Yes. Yeah, and the symmetries are generated by the reflections. These are reflection symmetries. In fact, they're called reflection groups. The Coxeter groups are reflection groups. And see, Coxeter wanted to, back in the 30s, wanted to deal with the problem of the characterization of crystallographic structures in spaces of any number of dimensions. If you're a physicist, you stop at dimension 3, generally, for crystallographic structures. But if you're a mathematician, you never stop at dimension 3. You want to go all the way, to dimensions of any number of dimensions, if you can pull it off, that is.
Yeah.
That's the ideal. And he was able to do this amazingly in the 30s. So he created a set of graphs that depict very, very precisely what crystallographic structures are possible in spaces of any number of dimensions. And the most important and the most useful of these graphs are the A's, the D's, and the E's. Mm-hmm. There's an infinite number of A's, there's an infinite number of D's, but very interestingly, there's only 3 E's, and the 3 E's correspond to actually, in a certain way, to Platonic solids. The E6 corresponds to the tetrahedron, and E7 corresponds to the cube and the octahedron that are dual to each other, therefore they have the same symmetry structure, and E8 corresponds to the icosahedron and the dodecahedron, which are dual to each other. Mm-hmm. So all 5 Platonic, these are called the Platonic solids, because Plato talks about them in more than one of his dialogues, especially the Theaetetus, and actually Euclid, writing years later, ends his famous book with a proof of the 5 Platonic solids are the only possible symmetries of that type. Mm-hmm. So what I'm claiming is that the E7 reflection space is in some sense the space for universal consciousness. Why? Because it's the overlap between two different algebraic and physical structures that strongly suggests that. And in other words, there's a kind of a universal body and there's a universal mind, and then there's an overlap region which really controls them both in some sense. Mm-hmm. And in order to see why, one would have to go deeply into quantum mechanics, actually, because quantum mechanics is very basic to this whole picture, but it's hard to describe just in words. When
but one of the points that
a long paper describing it.
One of the points you make about reflection space mathematically is that it's analogous, probably in a meaningful way, to the idea of reflection in consciousness.
Yes, that's something I wrote about in that paper. Yeah, and it's true. We might think of it as a metaphor, but it's a metaphor that in a way cuts both ways. That reflection, in fact, various philosophers have suggested over the years that thought fundamentally is reflection, and I don't know how seriously they took that metaphor, but some more seriously than others probably. But here I'm making a very detailed mathematical physics argument for that idea. And yeah, well, you see, the reflections in the reflection space are really the magical thing doing all the work, so to speak. Because when we say we have fundamentally a reflection group, well, that means that you have these mirrors, really hypermirrors, because in each space of any n-dimensional space, the mirrors have to be spaces of one dimension less in order to cut the space in half, which the mirror has to do. Because these mirrors, a reflection mirror this is a mathematical idea of reflection, by the way. This isn't the way ordinary reflections work. Ordinary reflections work by, as you know, bouncing light off of the mirror.
Right.
But if you're if you're Lewis Carroll, you want, and you write about Alice through the looking glass. Alice, went through the looking glass to see the world on the other side of the looking glass. So a mathematical reflection is exactly like Alice's magic looking glass. In other words, what mathematical reflection does is it flips everything from one side of the mirror to the other side and vice versa. That's what a mathematical reflection is. And of course, if you have a set of basic mirrors in a space, if you have a 7-dimensional space, then you have 7 basic mirrors, but they create through reflection, create virtual mirrors, and all the reflections go through all the mirrors, but they're fundamentally created by the 7, in this case, 7 basic mirrors. And the thing is that these reflection points are very related to quantum mechanics in the sense that they are actually what we in quantum mechanics we call the eigenvalues. Mm-hmm. See, in quantum mechanics, one very basic idea is that when you make a measurement, you find a specific state, call it a state vector. The state vector is the mathematical representation of it. But you don't really see the state. What you see are what we call the eigenvalues that correspond to that state. It's an eigenvalue, like, for instance, electric charge is an eigenvalue, okay?
It's something that is actually observed, is it not?
Is an eigenvalue, yes. Mm-hmm. And the interesting thing is that the points in the reflection space are eigenvalues. The states are actually the basis vectors of the algebra involved. Okay.
Well, it sounds okay, but it's hard for me to understand a term like basis states.
Well, a basis. Okay. Well. Okay. In 3-dimensional space, we talk about X, Y, Z coordinates, right?
Right.
So to set up X, Y, Z coordinates, we have three vectors. Call them X vector, Y vector, Z vector. Yeah. Those are the basis, what we call basis states of a 3-dimensional space.
Right.
Okay.
Mm-hmm.
And like in space-time, you have an extra one called time. Okay. Actually, we multiply the time by the speed of light in order so that they'll all be in agreement that they're all describing distance. Okay.
Okay.
And so those are the ordinary, simple mm-hmm. examples of basis states. But any vector space of any number of dimensions that has, if an n-dimensional vector space would have to have n basis states or basis vectors, mm-hmm. Which generate the entire vector space. In other words, every point in the space is described in terms of the basis vectors, and any point in the space is also corresponds to a vector in the sense that you take that point and you draw a line back to the origin.
Yeah.
The origin is where all the basis vectors cross, by the way, they originate.
Well, here's my question. If we're talking about hyperspace, and we're talking about eigenvalues, an eigenvalue, if it's actually observed, how do we observe an actual value if it's not in 3-dimensional space? Or 4-dimensional space-time? How can we make an observation in a higher dimension of space?
Well, the higher dimensional structures are projected down to lower dimensional structures, and this is implicit actually in these Coxeter graph diagrams, because the higher dimensional structures, and this is true for crystallography, the higher dimensional crystallography, the higher dimensional crystals project down to lower dimensional crystals, and the same goes for eigenvalues and eigenvectors. So in other words, what we see in three-dimensional space always, from this point of view, is really a projection from a higher dimensional space. Now, actually, this idea of reality being a higher dimensional structure that projects down to a lower dimensional structure is implicit in Plato, in Plato's famous cave analogy, or cave story about people that are chained in a cave in such a way that, and there's a light behind them, some torches or something, and they see their shadows on the cave wall, and they identify themselves with their shadows because they're chained in such a way that they can't even move their head. This is just a thought experiment of Plato's. Yeah. And it seems to me that that's my phone ringing. It seems to me that Plato is suggesting that we, three-dimensional creatures, we identify ourselves with our three-dimensional bodies, but that we're actually higher dimensional entities, living in some higher dimensional, what we could call Platonic realm, in fact. And that, many people have suggested this way of interpreting Plato's famous cave story in the Republic, Book 7 of the Republic. And every college student probably is required to read the Republic at some point, since it's considered basic in some sense to Western civilization.
But in effect, you're suggesting that human consciousness could be like this, that let's say at the death of our three-dimensional body, a hyperspace consciousness will continue.
That's correct. Yeah, that's correct. And of course, Plato very much believed in this kind of immortality of the soul, he might call it. Psyche is the Greek word that he would use. Psychology is based on that word, by the way. Psyche. Apparently he'd gone through exercises, mystical exercises, which convinced him that the soul lived on after death. The so-called Eleusinian mysteries outside Athens, there were many mystery schools, but that was the one that had very high prestige in Plato's time. And he went through it, and maybe Socrates went through it, I'm not sure, but certainly Plato did, and many other important people in Greek times.
Pretty much, to my knowledge, all of the leading citizens of Athens went through the Eleusinian mysteries, and we know very little about the details of what happened because they were sworn to secrecy. But my understanding is they all came back convinced of the immortality of the soul. Yes, that's correct. That's what the historians of that period tell us, and of course they wrote about it. They didn't reveal any secrets. They just said, "Well, I'm convinced of this, that, and the other," and they didn't say why. Yeah, but now you're basically arriving at a similar conclusion based on your interpretation of contemporary physics and mathematics.
That's correct. Yeah, that's correct. And I push that very strongly in the paper that is in your book, the appendix paper.
In fact, I'm linking to it right now. So if viewers want to read that paper, if you click on the upper right hand of your screen where it says click here now, it will take you to a PDF version of Saul-Paul's appendix. Well, Saul-Paul, I think we've covered a lot of ground here. We're off to a really good start. I know we have a lot of other topics we can cover. But I'm very happy that we did this, and I look forward to having many more conversations with you.
Yes, it was fun, Jeffrey. Thank you.
Thank you for being with me. And I want to thank our audience as well for being with us.
Book 3 in the new Thinking Aloud dialogue series is UFOs and UAP, Are We Really Alone? Now available on Amazon.
You can now download a free PDF copy of issue 7 of the New Thinking Aloud magazine or order a beautiful printed copy.